Hello everyone, in today's video we're going to learn how to work with the properties of exponents, also known as exponent rules. This is a classic in mathematics. You're going to see it on almost every high school course. I think you will see them in every high school course, and certainly at the first few years of university math. They're one of the key concepts that connects a lot of things together, so it's very important that we cover them. What you see here on the screen is the solution set. What we're going to do together is we're going to cover the student version of these rules, cover a few examples to eventually leave you with a few exercises to practice on your own. Don't worry, this solution is going to be posted in the description below, so you make sure to check that out. If you're new here, my name is Olivier and I'm a certified math and physics teacher in Ontario who is currently doing a master's in statistics at Carleton University. I just inserted this PDF into OneNote so I can write on it. I could have done it in Microsoft Edge, but I find OneNote a little bit smoother and I'm more used to it. Just a reminder that if you hear some Velcro noises, it's because I have a cast on. I have a broken hand, so my writing might not be optimal here. Let's get to it. We have the theory of the exponent rules. The main concept for exponents that I want you to take away is that really exponents, it's just short form for multiplication. So it's short form for multiplication. That's not bad for a broken hand. But what does that mean, right? It's all nice that we know a sentence, but we have 2 to the 5. Let's say we have 2 to the 5. That means that this is 2 times 2 times 2 times 2 times 2. It's repeated multiplication. How many times in total? 5 times. So the 5 here means that we repeat the multiplication of whatever's at the bottom 5 times. So note that I said whatever's at the bottom. So 2 to the 5, there's a name for that. That's a base. So you can remember it, the way I remember it personally is it's at the bottom, so it's the basement. So that's how I think about it. And the base is usually the foundation, right? And the red thing, the 5, is the exponent. So that's the exponent. Exponent rule, so it's when we have a number that's raised on top of it like that. And the whole thing, not many people know this, but the whole thing, so 2 to the 5 is called a power. This is a little bit less important to know, but it's just nice to know since we're already learning it. So the whole thing is called a power. So now let's cover the rules and let's see an example for each one. And after that, you'll be left with the exercises. So the first rule we're going to see is when we have a to the x times a to the y. So when we have the same base, so note that a and a here, so the same base, that's a key concept. So same base. Well, what do we do? When it's multiplied, we add the exponent. So it's x plus y. So what does that mean practically? We have the same base here. We have 2 to the 4 times 2 to the 2. So the same base is the key thing. So what do? Well, it's 2 to the 4 plus 2. We add the exponent. So it's 2 to the 4 plus 2. So then that would be 2 to the 6. Before we get further, we could calculate this. This is really 2 times 2 times 2 times 2 times 2, 6 times. So that would be 64. All these rules that we're going to see should be intuitive if you remember the top part of repeated multiplication. We have 2 to the 4, right? So that's 2 times 2 times 2 times 2, 4 times. So 4 times. And then times 2 to the 2. So that's 2 times 2, right? So that's 2 times. How many 2's do we have in total? Well, we have 6 of them. So that's 2 to the 6. And to do the math, there's many ways to do it. That would be 4 times 4 times 4. So that's 16 times 4, which is 64. But personally, what I remember is I just remember 2 to the 5 is equal to 32. That's like my memory thing that I remember. So 2 to the 5 is 32. because that's kind of in the middle. 2 to the 3, you can still do it by hand or in your head. That's like 2 times 2 is 4 times 2, that's 8. But 2 to the 5 is like high enough that it gets you all those low ball powers of 2. So that's when we have the same base and we multiply. Now if we move to rule 2, we can see that we have a division. So what happens when we have a same base, but instead of multiplying and adding, well, it's division, we subtract them. So again, that should be intuitive, but let's do the intuition later. Here we have 3 to the 7. So we will do 3 times 3 times 3 times 3 7 times. So I'm at 5. Need 2 more. I think that's 7. And then over 3 times 3 times 3. Note what happens. Boom, boom, boom. They all cancel. And then I'm really left with how many 3s? That's a repeated multiplication of 3, 4 times. So I'm left with 3 to the 4. Or if we did it the other way using the rule, it would have been a subtraction, right? So it would have been 7 minus 3, which is 3 to the 4. And now we can do the actual math. So then 3 to the 4 is simply 9 times 9. That's one way to see it because it's like the 4 3s. So that would be 81. Okay? So that's the key thing here. And don't worry, all of this is written nicely in the solutions if I ever went a bit too fast or my writing is too poor. So rule number 3, we have a negative exponent. What do we do when we have a negative exponent? We put it in the bottom and make it positive. So if the power is on top, if it's in the numerator, we put it in the denominator and we make the exponent positive. So what does that mean? Here we have 4 to the negative 2. That would be 1 over, so we put it in the bottom and make it positive. Now what is 4 to the 2? That's simply 4 times 4. So that would be 1 over 16 as a final answer. So that's one way to see it here. And the same is true. So these two rules kind of go together. It's just a negative exponent rule. So what we have is, if it's in the bottom, if we have a negative exponent in the bottom, then we put it on top in the numerator and make the exponent positive. So what would that look like? Well, here we have 1 over 5 to the negative 3. So we put it on top and make the exponent positive. That's really 5 times 5 times 5. That's 25 times 5. So that would be 125, I think. That would be 5 quarters, so that's $1.25. So that's how we work with negative exponents. We just put it on the other side of the fraction and make the exponent positive. Now, if we move on to the next rule, this one is interesting because it relates to the other ones. We have a power of a power, and that's a very common one, okay? So what we do is we multiply the exponents, so then it would just be 2 to the 3 times 2. So that's 3 times 2, so that's just 2 to the 6. Now that's a big fraction that you need to calculate. But recall, 3 to the 5 is 32. So 3 to the 6 is really 32 times 2, because it's one more 2 than 3 to the 5. So that's just 64. And we did it earlier, so you could have remembered from that. But that's not the concept I want to teach here. The concept I want to teach is really 2 to the 3 squared. So ignore the 2 to the 3. Let's say we have something squared. What does that mean? Something squared means that we do that something multiplied by itself 2 times. That's what exponents mean. So now if I put 2 to the 3 in this imaginary box, really it's like I have 2 to the 3 in there. So what that means is I have 2 to the 3 times 2 to the 3. When we have exponents, powers with the same base, what do we do with the exponents? We add them. So that becomes 2 to the 3 plus 3, which is 2 to the 6, which is also 64. Okay, so that's the key concept. Exponent rules are all connected, so that should make a lot of sense here. For the next rule, again, this one is connected. It simply says that when there's no addition inside, when it's all multiplication, we can apply the exponent to every base inside. So it would just be a to the x, b to the x. So we can distribute the exponent like that. Note that this only works with multiplication. It won't work if you have a plus or minus sign in there. So if we apply this rule, we have 2 to the 2 times 3 to the 2. 2 to the 2 is 2 times 2, so that's 4. And 3 to the 2 is not 6. A lot of people say 6 here. It's 3 times 3, 2 times, so that's 9, right? So that's 36. Note that there's a couple of things I want you to note here. One is that if we just applied BEDMAS, we would have had 2 times 3 squared. So BEDMAS, that's brackets first, so that's 6 inside. 2 times 3 is 6 squared. Then 6 squared is just 36. So that's the first thing here. The second thing is that if we have 3 times 2, 2 times 3 all squared, that means that this is, anything squared is times itself. So really we have 2 times 3 times 2 times 3, and then this is 6 times 6. Or you could rewrite them to put the 2's together, which would give 4, and the 3's, which would give 9. 4 times 9 is 36. So again, all of these methods give 36, but I'm showing you this so you get a feel for exponent rules. That if you don't remember them, you can derive them with the very basic concept of what is an exponent. The same is true for the next rule. It's really the inverse of the top rule. So when it's all multiplication or division, we can simply distribute the exponent to both. When there's a plus or minus sign, it won't work. I'm warning you right now. So we just distribute the exponent to both. We have 3 squared over 5 squared, so then that would be 9 over 25. I can't simplify this. Now let's do the other method, because we have something squared. So then that would be anything squared is times itself. How do we multiply fraction? Well, you can look at the video appearing in the top right on multiplying fraction. We multiply across. So we multiply these numbers together. So that's 9 times 9 over 25, and you see that these two fractions are the same. The same is true when we have a fractional exponent. It's really a square root. And note that when it's like a cubic root, we write 3 and then the square root. But a square root, we don't write the 2 because that's the most common one, but technically there is a 2. That's like an nth root, or here it's a yth root. But here it's a square root, so I'll just write it here, but we don't need it. The key thing is exponent 1/2 is square root. That's the key thing. And we're going to connect a few dots here after. So we have 4 to the 1/2. What is that? Well, that's just the square root of 4, which is obviously 2. Hint, hint. This, your whole life, you've been told that if you're solving equations, if you have a plus sign, you do a minus sign. If you have a multiplication, you do a division. If you have a square root, you square the thing. Well, that's why, because they're opposites, they're inverse operations here. We have square root and squared. And the same thing will be true when we have logs. So the way to get rid of like log 2, for example, log base 2, is to raise it. The base will be 2, and you raise the whole thing, and that will cancel. Now let's connect this concept to not just the square roots, but the nth root, and even when the a has a power here. So this is really what we're talking about. This would be the same thing as saying it's a power of a power, really. So we'd have a to the x to the power of 1 over y, and it's a power of a power, so we multiply the exponents, so we'd have x times 1 over y, which is just x over y. That's all we're doing here. So if we have 8 to the 2/3, really what we have is we have 8 squared to the 1/3, and then 8 squared is 64 to the 1/3. What is to the 1/3? Well, it's the cubic root. Now, what is the cubic root of 64? The cubic root, the question you need to ask yourself, what number times itself 3 times gives 64? The answer is 4, because when you multiply 4 by 4, that's 16. 16 times 4 is 64. The easiest way to do this usually is to do the cubic root first, because then the number simplifies smaller, right? So we have 8 to the 2/3 is equal to 8 to the 1/3 squared. What is 8 to the 1/3? That's the cubic root of 8. What number times itself 3 times gives 8? The answer is 2. So we have 2 squared. So that's 4. So there's 2 ways to do this, and I prefer the one on the left personally. You work with smaller numbers, and here all the numbers are relatively small, but sometimes it's going to simplify quite nicely one way and pretty ugly the other way. Now if we move on, anything to the 0 is 1. So 8 to the 0 is 1. How can you think about this, connecting the dots? Well, if you have, for example, 7 to the 2 over 7 to the 2. There's 2 ways to see this, or there's probably more ways to see this. If you remember, when we have the same base and we divide, we subtract the exponent, so that would be 2 minus 2. So that would be 7 to the 0, which is 1. We know it's 1. Or you could see that 7 squared is 49 divided by 49. And that's just 1. 49 divided by 49 is 1. And anything divided by itself is 1. So that's how you could kind of derive this one. So if you have a to the n, then you'd have like n, like a n times on top, and then divided by a to the n, it'd be always itself divided by itself would be 1 here. So 3.14 to the 0, well, note that, like, first of all, it's not just the 4 that's the 0, it's the whole thing. So then that would be 1. Negative 3 all to the 0, that would be 1 as well. Here, negative 3 to the 0, it is 1 as well. Nope, I caught you there probably. Hope so, kind of hope not, I didn't. It's negative 1. Why? Because of BEDMAS. Without a bracket, the exponent only applies to the base. If you have a negative, it's really like you have minus 3 to the 0, so then that would be minus 1. So the answer for that one is minus 1. The 0 only applies to the base and not the negative on the outside unless there's a bracket there. Now, lastly, this one is a little bit more trivial. Trivial took me a long time to know what that word meant. Just means that there's only one solution, or it's obvious. Anything to the 1 is itself. So when it's to the 1, it's just itself. So for example, if you have 7 to the 2 divided by 7, that's just going to be 2 minus 1, so that's just going to be 7, right? So, and you could see it as like 49 divided by 7 is 7. There's many ways to see it again. So here it's going to be 0.17. Let me write it in black. So this is just going to be 0.17. And pi to the 1 is pi. Note that this pi here is a number. It's not a variable. A lot of people confuse it as a variable, but still, it would still be pi if it's a variable, but it's a number. E, by the way, is 2.71-ish. That's another natural number that goes on forever. Now, let me catch you with something. A plus B squared. Based on the rules, you've learned that maybe you could do this. But no, you can't. It doesn't equal A squared plus B squared. Why? Well, it's because A plus B, if you think about it, what is an exponent? Exponent 2 means that you just multiply it by itself 2 times. So we have A plus B times A plus B. Now when you have 2 binomial terms, you know that you would do something like FOIL. So you multiply the first one, so I'll just write F. You multiply the outside one, so that's O. And then you multiply the inside one, so that's I. And then the last one, so L. So then that would just give you A squared, A times A, plus AB, plus BA, plus B squared. So then when you simplify, it's A squared plus 2AB plus B squared. Note that these two here are not the same. So when you have a plus sign, you cannot distribute in. You cannot do that. Common mistake here. Lastly, you have 6 exercises that you can do on your own. Again, the solutions are in the description below. If you need more help, make sure to refer to the Khan Academy section on exponents that you'll see appear in the description as well. And if you've enjoyed this video, make sure to check out the other Math Fundamentals video. As always, thank you for watching, and I'll see you next time with Do the Work.